we looked at how we can calculate experimentally delta H for a reaction. And that delta H, the change in enthalpy, is for a particular reaction with particular coefficients. If the reaction changes, then delta H is also going to change. So let's think about this. If I burn, say, 1 gallon of gasoline, it's going to give off a certain amount of energy. If I burn 2 gallons of gasoline, how much more energy is it going to give off? Twice as much, right? If twice as much reacts, then you have twice as much energy change. So that's what this is saying, is if we multiply a chemical equation by some factor, it's usually a whole number, 2, 3, 4, or divide it by 2, 3, or 4, then we do the same thing to delta H. So here, instead of gasoline, if we're reacting 1 mole of A and 2 moles of B, and this is the amount of heat that changes, if I double this by multiplying all the coefficients by 2, then the heat released or gained is going to be twice as big. If we run a reaction in the reverse direction, which is not always possible, but if we run it in the reverse direction, then if it was giving off heat before, now it's absorbing heat. So if we reverse the reaction, we change the sign. So this is like the buying and selling, right? It's the same number, but whether it's positive or negative depends on whether you are the one buying or you are the one selling. You do the opposite transaction and the sign changes. So when we take this chemical reaction and we write it in reverse, so now that product C is the reactant, and we're taking that apart into A and B. Delta H is the same, but a different sign, the other sign. And then Hess's law tells us that if we can express a chemical equation as the sum of a bunch of different chemical equations, then we can find delta H for that final equation by adding up the delta H's for each of the steps. So the idea here, we've got that A plus 2B making C. This has a delta H of some value. If we have another reaction where C is going to 2D, that's going to have a different delta H. If we add these two reactions together, so we're adding equations. This is forming C, and this is using the C up, and so that doesn't show up in the picture anymore. And now we have A plus 2B goes to 2D. Then delta H for this reaction is the sum of the reactions that we added, because we did this one and that one. Or we can look at it in an energy diagram like this. So here's the starting point, and I can describe the reaction to form C as being an increase like this, and then C going to 2D is a decrease down here. Enthalpy is a state function just like altitude. So remember the mountain, oh, I made that too long. Remember the mountain climbing example? And we can go up the windy path that was farther, or we can go up the side. Here what we're talking about is going down. So, maybe you could ski down the side, or you could hike down the windy path. Your change in elevation is going to be the same no matter how you got there. Well, this is me preferring to take a helicopter, right? So I'm going to get in the helicopter here. It's going to take me up to this elevation. We're going to move over a little bit, and then it's going to take me down to the base of the mountain. The change in elevation is the same. It doesn't matter how you get from one place to another. So that's why we can do this. Questions? why would we want to do this? Well, some chemical reactions would be really hard to measure delta H for in the lab. And so instead of trying to figure out how to measure a delta H for a difficult reaction, we can see if we can find other chemical equations that we can add together to get the same overall equation. And if we can do that, we can look up delta H for each of those reactions, and we can combine them, and we can get delta H for the difficult to measure reaction. So let's practice these relationships a little bit. So this is that same one, or is it? I don't know. This is an equation. Doesn't matter. 2A plus B making C. And we're told that delta H for this is 122 joules. The question is asking us, what's delta H for 2C going to 4A plus 2B? So we need to think about what happened to this chemical equation to make it look like this. There's two things that happened. Pardon me?
It was flipped and multiplied by 2.
There's a multiplying by 2, right? So here the coefficient for A was 2, and over here it's 4. Here the coefficient for B was 1, and now it's 2. This was 1, and now it's 2. So twice as much stuff is reacting. So then I need to take my delta H, and I need to multiply by 2 because I have twice as much material reacting. What's the other thing that's different? It's flipped. This has C as a product, and this is reversed. It has C as a reactant. So that means the energy is going the other way. So then I multiply by -1. So for this reaction, 122 times 2 would be, I don't know how I do that, 244 joules, and then times -1 would make it -244 joules. Does that make sense? Twice as much stuff reacts, twice as much energy is exchanged. If I do an exothermic reaction in reverse, it's going to suck in the same amount of energy it gave out in the forward direction. So this is a Hess's law problem. So we are trying to find delta H for this reaction, and we are given these 3 chemical reactions, and the delta H is associated with them. There are probably thousands of reactions like this. Just in the CRC, which is that fat book on the shelf over there, you can go look these up, because people have measured delta H for every reaction they could think of. So you can go look that up. So what we need to do is we need to figure out how can we combine these 3 reactions, these 3 equations, to get this equation. Now this one, there's N and O all over the place, and N2O and NO2, so easy to confuse those. So I'm going to make it into colors. So N2O is going to be highlighted in yellow, and that's that one down there. And looking around, that's the only place N2O shows up. And then NO2, I'll make that one blue. And so then I'm going to look through my other reactions over here, and where do I see NO2? It's right here. Is it anywhere else? No. And then this is one of my favorite molecules. No! It's all caps. It's yelling. So I think red would be a good color for that one. Well, where is no? No is here and here. Now, we've got some things in these other equations that are not in our final equation, If we combine these correctly, then these things are going to cancel each other out. And this is much simpler than just being given the CRC and being told to do this, right? So we're setting you up for success. We're giving you all the equations you need and only the equations you need. So we're going to use all the equations, and we won't need anything else. Okay, there are different ways to approach this. What seems most organized and straightforward is just to start with the first reactant. That's this yellow one, N2O. And I want to find a chemical equation down here that has N2O in it, and I need it to be a reactant. If it's in the product, then I'm going to reverse the reaction. If it's in the reactant, I can just leave it alone. So here, I have N2O gas as a reactant. So I'm going to start with that one. N2O gas, there's two of those. And that's going to go to 2N2. Whoops. Plus O2. And that's my N2O. Did I change the chemical equation? I didn't multiply by anything. I didn't switch the order or reverse the direction. So delta H is the same. It doesn't change.
And we're saying that because why again?
So I just copied this here. I didn't change coefficients. I didn't change the direction. So this equation is the same as that equation, and so delta H will be the same. Because it's the same equation, same reaction. Let's find the blue one, NO2. Well, only one of these has NO2 in it. That's this guy. So this is the equation I'm going to use. But here, NO2 is a product, and I need it to be a reactant. So I'm going to reverse the direction when I write this. So I'm going to get 2NO2 gas, and that's going to make 2 no plus O2. So there's my NO2, and here I have my red no. I changed the equation, the chemical equation. I reversed it, right? So when we reverse the equation, what do we do to delta H? We change the sign. So it was negative 113.1 kilojoules. In reversing the sign, I'm going to multiply by negative 1, and that becomes a positive. Well, now we have the right colors on the right sides, but we got all this nitrogen and oxygen over here, and they don't seem to be canceling out, so we probably need the third equation. So that's this guy in the middle. That one also has no. It has it as a product, so we're going to write that one down. 2N2 plus, N2 gas plus O2 gas gives me 2. No. We have a puppy in our house, and I think we should have named the puppy No. That's probably what he thinks his name is. Did I do anything to the reaction? Did I change it? No. So I'm not going to change delta H. I'm just going to copy it down. 182.6 kilojoules. Now I need to look at this. I might need to multiply or divide to get all of this to work out. So I want the highlighted ones to stay, but I want these other guys to cancel out. I've got 2 moles of oxygen over here and 2 moles of nitrogen, but over here I only have 1 of each. We could multiply by 2. So let's multiply that bottom equation by 2. This becomes 4. I'm multiplying the equation by 2. What do I multiply delta H by? Same number, 2. Okay. Let's see if we can have this work out now. So I've got 2 N2 over here and 2 N2 there. So those are going to cancel out. And here, 1 oxygen plus 1 oxygen, that's a total of 2 over here, and there's 2 over there, and so I can cross those guys out. It's a little bit like adding the half reactions, so the electrons cancel out. I'm going to copy down, maybe not in red. I'm going to copy down what's left, so I can see what's going on. Now, in the products, I have 4 no's down here and 2 no's up there, so that's 6 of them. 6 no. Let's highlight those so we can see what they are a little better. So that's pretty close to this one, right? What's wrong? The coefficients are wrong. This is coefficients of 1, 1, and 3. This is 2, 2, and 6. So this is twice as big as I need it to be. I forgot to add these up. I'm going to add up the delta H's, negative 163.2. Plus 113.1 plus 182.6 times 2. Yeah, that's kind of high. So those relationships talked about multiplying and mentioned dividing. Well, I could think of this as multiplying by 1/2, right? I think most people would prefer to divide by 2. So if I divide this equation by 2, so divide by 2, this becomes a 1, that becomes a 1, 6 divided by 2 is 3, and then I also divide this by 2. Because what I had come up with here was twice as much reacting. So I'm going to divide by 2, and then I'm going to get my answer. Delta H for this reaction is 157.6 kilojoules.
So when we go and cross out in the equation, the coefficients don't have to be the same with the products and reactions?
Can you clarify that?
You know, on the third equation,
Mm-hmm.
the reactant side, there's 2 O2s. The only reason why we're able to cross it out because there's 2, because we crossed out 2 of them? Is that
Because the sum over here
why?
is
Because
2.
there's 2 of them in general.
Yeah. So if I'm adding all of these together, this is 1 plus 1, there's going to be 2 of those. Yeah. Any other questions?
What's the purpose of this again? Why do they do it?
The purpose of this is so you can find the heat of reaction for a reaction that maybe someone hasn't studied before or that is not possible to do in the lab and measure. And the good thing is, we're going to talk about 2 other ways to find this that are easier. So, but this idea is very important. This tells me that this equation, if I do this reaction, I'm going to get this much energy for 1 mole of that. Does that reaction actually follow this path? Is it actually a combination of these 3 equations? Those 3 reactions? It doesn't matter. Because it doesn't matter if I take a helicopter off the mountain, or I ski straight down the side, or if I toil and go down that steep, windy path. It doesn't matter. Let's do another one. This one only has 2 equations. Find delta H for this reaction. Okay, I'm going to highlight things again. I think water should be blue. So I'll highlight all the waters as blue. Oxygen seems kind of, oh, that's not oxygen, that's ozone. I'm going to make ozone orange. This is ozone. And there's ozone right here. So O2, O3, right? Easy to mix those up. And then maybe we'll make hydrogen green. And so hydrogen's right there. I think it just makes it easier to see what we're trying to get to. So I need to have hydrogen on the reactant side and water on the product side. This first equation has both of those. So let's start with that. H2 gas plus O2 gas to make 2 water in the gas state. And I didn't change anything in the equation, so I don't change anything in delta H. So there's hydrogen, and here's the water. The coefficients are not right, but let's worry about that later. I need ozone to be a reactant, and here ozone happens to be a product. So I'm going to reverse the direction for that equation. So I've got 2 O3 gas is going to make 3 O2 gas. And what do I have to do to delta H there? I reverse the reaction, multiply by -1. So this becomes negative 285.4. So I got everything in the right places. Now I need to get rid of the things that aren't highlighted. I need to get rid of the oxygens. And I ultimately want to get the coefficients to match this equation. Well, this side has 3 oxygens, and that side has 1. We want 3 as the coefficient for hydrogen, and we've got 2. We could multiply by a fraction, but I'm not going to because I think it's harder that way. So if I multiply this top reaction by 3, then my oxygens will cancel out. Yeah? So this will be, times 3. So this becomes 6, and that's 3, and this is 6, and then I'm going to multiply this also by 3.
So what you do to equation, you have to do the delta H too.
Yeah, whatever you do to the chemical equation, you do this essentially the same thing to delta H. If you multiply by 2, you multiply delta H by 2. If you divide by 3, you divide by 3. The one thing that's just not exactly the same is switching the direction of the reaction is changing the sign on delta H, because that's like going from buying to selling. You're switching the direction of the transaction. So I got these so that they're going to cancel out. So let's just add this up and then worry about the coefficients. So 6H2 gas, the O2 canceled out, 2O3 gas, I'm going to end up with 6H2O gas. And then let's look at delta H. Negative 483.6 times 3 plus negative 285.4. Delta H for that one is negative 1736.2 kilojoules. I have the correct reactants and product, but the coefficients are wrong. I need this to be a 3 and that to be a 1. I have 6 and 2. So let's divide by 2. So I'm going to divide this one by 2. So that becomes 3. And this becomes 1. And this becomes 3. And then I'm going to divide this by 2. So negative 1736.2 divided by 2. Delta H for this guy is negative 868.1 kilojoules. We could have done this in one step by multiplying by 3/2, but if you like stuff like that, you don't need me to explain how to do that. Any questions? How's this law?
So we can't add up the delta H's we can't touch the coefficients until we add up the delta H's, right?
I think it's best here to add up the delta H's and then mess with coefficients, because you've got all of this figured out, and then you can just apply the same thing that you did over there. But there are other ways to get to this correct answer, and I've gone through a couple different ones over the course of teaching this several times, and this is the one that seems to make the most sense for most students.